Okay, let's start with the result we got last time, and then we're gonna work back and talk about complex numbers and work our way through this problem again. We got plenty of time, and this stuff is very interesting. So what we had last time was a step function defined from minus pi to pi. Now you would never have any hope at all. You'd never have any chance to expand that thing in a Taylor series. Yeah, we just did expand it in a Fourier series. So what was our result here? This was our x-axis, this was pi minus pi. We had the step function. If we called it f of x, it was equal to -1 from minus pi less than x less than 0, positive 1 from 0 from x less than pi. Okay. So no chance to get that in a Taylor expansion. What we did find was f of x, and you guys help me out here. What did we have? 4 over pi?
Sine x, yeah.
Yeah. So 4 over pi was a common factor here. Then we had, so I'll factor that out. We had sine of x plus sine of 3x over 3. Plus sine of 5x over 5. And then the pattern was cleared. Okay, so we had an infinite series there. And how did that come about? Okay. How did that come about? So that was all the way out to infinity. You know, maybe before we go back to that, what if we try to put this into closed form, just as a summation? That's always a good exercise. So we would have a 4 over pi, and we would have sine of, we just have the odd powers, so we could have 2k plus 1 divided by 2k plus 1. And in that case, we can go k equals 1 to infinity. That probably does the trick right there. Okay. We got the 0. Very good. Got ourselves a 0. What would I have to do if I did start with k equals 1? I'd have to have 2k minus 1. Right, you got the same. Good. So be that as it may, how did that happen? That's the question. And what we had was, so we kind of work our way backwards. We had the question, what if we can expand a function in this form here? We have a c sub k e to the I kx, k equals minus infinity to plus infinity. And so you notice the result was real. We started out with a bunch of complex numbers. So those steps that I did in the proof last time, it would be good for you guys to review those. And what we had found was that the c sub k is going to be 1 over 2 pi integral minus pi to pi f of x e to the minus I kx dx. And that's what we actually integrated last time. And I had even pointed out a couple of things here that just based on this definition, know that the c sub negative k is equal to the c sub k complex conjugate. So I replace k and negative k, it's the same as replacing I with negative I. So that's one of the first things we have to get used to with the complex numbers. Those kinds of relations here. So that's what I want to review. In the recitation, we did these two problems yesterday, and I'm pretty sure we'll talk about those today as well. And those two problems that had been assigned are very good practice for just the nuts and bolts of complex numbers. For example, this type of thing. So what I'm going to do is just briefly mention what's on that, okay, for the record, so to speak, and just for review. And then we'll return to exactly this thing here and explore it a little bit more. So there were a whole bunch of interesting steps going from the integration. You know, we could plug this in here, broke it down into two integrals. And at some point we recognized that we had that sign of x in there, because remember we had a bunch of complex exponentials. We recognized the certain form that it was assigned and took it from there. So let's talk about these complex numbers again a little bit. So once again, it's just complex number review with a look at what's important. So we've got these complex numbers, the set of z equal x plus iy, x and y are real, y squared equals minus 1. Okay. And we can do a couple of these things with this, but just kind of listing these. And you know, we have addition, subtraction, multiplication, division. Works really well. A very important property here is the z complex conjugate, which is just defined as x plus iy complex conjugate, since it's my complex number, and just x minus iy. So the one thing, you're always just, for the complex conjugation, you're just placing I with negative I. The reason this also holds true in a, say, e to the ix, is that e to the ix is actually a series expansion, and you can replace I and minus I in every term of that series. Okay? So that works. The other thing we need is the magnitude of a complex number, and that is the square root of z star. Okay. And if we say what is z times z star, we've got x plus iy, x minus iy, and when we multiply that out, the cross terms vanish or cancel, and we end up with root x squared plus y squared. And often when we're doing work with these, we have z squared just gets rid of the square root x squared plus y squared. So very important to note here that this square here is not equal to z squared. You have to be very careful with that. And when you're working with complex numbers, the magnitude is going to have this important definition up here. And because we just did z complex conjugate squared, we've got x squared plus y squared. And over on the right here, we have x plus iy quantity squared, which is x squared plus 2iy plus y squared, x squared plus y squared plus I times 2xy. And they're clearly not the same. So that's something to pay attention Now, when it comes to doing what we did over here, and we got the signs out of there, remember we had e to the this and that, and we ended up with the signs. There we made use of the property that the real part of z is quite generally z plus z complex conjugate divided by 2. And the imaginary part of z, just by the definition, z minus z complex conjugate divided by 2I. So for example, when you have e to the I kx equals cos kx plus I sine kx, so we have Euler's formula here, then if we add e to the I kx plus e to the minus I kx, in fact, let's go ahead and write this, I kx equals cos kx plus I sine negative kx, but because the sign is odd, we can pull that minus I sine kx out. And then you see, if you add these two, I kx plus e to minus I kx, you get 2 cos kx. And so once you know that and have done it a few times, you're looking for it, and you can implement that. And if you subtract e to the I kx minus e to the negative I kx, you've got 2I sine kx left over, you divide it by 2I. You've got your measured part versus sine. So for that reason, these basic relations, you just practice them until you get used to them. Right? They're always in play when we're using complex numbers, but we don't need much more than that. Okay? So these basic rules will take us a long ways. Good, so there's that. And I'll erase this and rewrite it again. So when we come to those 2 homework problems that we're pretty likely to be discussing, one of them was just this triangle inequality. So z1 plus z2 magnitude less than or equal to z1 magnitude plus z2 magnitude. Right? And the first thing we were going to do here was square both sides. Okay? But here it has to be the constant. But, just to get rid of those square roots, we don't want to deal with those. So we'll still have the inequality if we square both sides. Here, of course, we have to z1 plus z2 squared less than or equal to, now the right side is just real numbers, plus 2z1 z2 plus z2 squared. Okay. So good, that's the right side. The left side, we have to write out z1 plus z2 times z1 plus z2 complex conjugate. Z2 complex conjugate. Let's read this stuff. So that's our first step. We have to do that, and then we'll recognize these, and we'll actually just have an interesting inequality between this and its counterpart on the left side. So we did that yesterday, and these are excellent examples to work with. All this stuff, really. So let's see. The other problem that's interesting in this regard, so if we can do these, we'll really have some good insight. Okay, I'm going to erase this, right? This was kind of a repetition. We had this on our other notes. The other problem, I'm going to draw a really large circle just so we can see graphically what it is we're looking at. So we have the unit circle. Okay. We're actually not interested in X and Y. This is the unit circle, and we defined sum of differences of complex numbers. Okay. I'm just gonna go to 3 of these. Okay. And we had this L sub n equals the sum over something. Okay. So those somethings there were the magnitudes of the differences of these complex numbers. So this was our 0th one. And so what you're seeing there, the difference of these two numbers is this directed segment. Because the complex numbers act just, or are just like vectors in 2D. So it's this little directed complex segment, and its absolute value has to be evaluated in terms of these rules here. And what you get is something that really simplifies. In fact, you get the same thing for each of these. It was like k equals 1 to n. You have it in your notes, right? It's homework problem. Each result that you got here turned out to be exactly the same thing, with good reason, because these have been defined symmetrically, they each have the same length. And so what you ended up with was, I'm gonna put this here, L sub n, since they're all the same, it turned into n times that thing right there. And in the limit as n went to infinity, you had more and more of these, and this little, what do you call it, polygon, turned into the smooth arc. It turned into the smooth arc. So yeah, we'll spend more time on this one, but it's just gonna implement all of these properties here. Okay, good. Okay, good. So now let's go back to the Fourier series. I'm going to repeat the calculation that proved the coefficient, and the next thing we're going to do is look at the real Fourier series. So once again, just to repeat what we had, if this f of x can be written as this sum, actually minus infinity to plus infinity, ikx. So if this is possible, then what we do is we multiply f of x by e to the minus I nx and integrate from minus pi to pi. So if this is an equality, then I must be integrating c sub k. Actually, let's go ahead and write it again. I must be integrating this entire right side, c sub k, e to the I kx, I'll just put k here. I'm multiplying this whole thing by e to the minus I nx, and I forgot my px right here, dx. So we're going to assume this works well, everything's well behaved enough, and if we had a finite sum, there'd be no arguing about this. So suppose we can interchange the integration and the summation. So now we would be looking at the integral e to the I k minus nx dx over all these k. And when we do this, we find that this integral here is either equal to 2 pi, if k is equal to n, because then I have e to the 0 integrated from minus pi to pi. Or it's equal to 0 if k is not equal to n, and these k's and n's are all integers in order for this to be true. Okay. K is not equal to n. So this calculation you guys should have a look at a couple times to make sure you agree with it. Okay. So what that does is it turns this whole thing into the sum of c sub k times 2 pi times chronic or delta kn, which is equal to, it's 0 everywhere except when k is equal to n. Then it's equal to 1, so that's why we get c sub 2 pi times c sub n. And that's the proof already, right? The c sub n, and we can now, you know, go back to k if we want, is equal to 1 over 2 pi times that thing. So this is a really stereotypical calculation, and you'll see later on in mathematical physics classes that this is done even when you don't know the name, or the, if you don't actually explicitly know this function, there are sets of functions that have this property. In this case, these complex exponentials have this property. So I'm going to make this property explicit for us. So what we have is one over 2 pi times pi b sub k of x b sub n of x star dx equals delta k n. So this would be the abstract property we're going to run into later on often. You have a set of functions that have this property that, you know, you integrate over them, you either get 0 or 1 in this form. So where b sub k of x is equal to e to the pi kx. That's exactly what I have in this step right here. Just to, you know, so this step here, is what I have here. This is the abstract form of it, which we'll return to then when we get to linear algebra and inherit all these results. Okay. Right now they're just math properties. Good, so we've done one of these. And we're going to do the real version of this. I'm going to assign this as a homework as well. Let's see. Yeah, I'm going to solve this. So for the purposes of the proofs and where we're headed with this material, we need the complex version. But the real version is going to be very useful as well. So there's no getting around it, we just need both. So the real Fourier series, it's going to look like this. F of x equals a naught over 2 plus the sum of a sub k cos kx, k equals 1 to infinity, plus the sum over b sub k sine of kx. So there's a real version of this. One of the advantages it has is you can pick off the special cases where you have an even or an odd function. Whereas with the complex case, we just had to go through the whole thing. What did we end up with? We had an odd function and we ended up with just the signs. So if you have an odd function, you're just going to have this part of your Fourier series. If you have an even function, you're just going to have that part. So we have that with a sub k is equal to 1 over pi minus pi f of x that. But do we have that? How do we prove that? I'm just making it up. And this one includes the a sub 0, by the way. These only have the 1, right? So this would be k equals 0, 1, and so on. Here k is just 1, 2. So the proof of this actually is just the rearrangement of the c sub k's that we had before. So the one we just did before with the complex numbers, we proved fair and square. And so what we can do is demonstrate that these things hold true. Anybody see how that might be done? So how could we, I'm gonna put this as a homework, but we'll just get started on it together because it's a good thing. The homework, show that, you know, star, 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 that these equations follow from f of x, sum of k, c sub k, e to the I kx, 1 over 2 pi. Minus pi to pi, f of x, e to the minus I kx dx. So they follow from those formulas again, which we have up there. And the way we'll do this, what do we have for c sub 0? C sub 0 is just 1 over 2 pi f of x dx. Because when k is equal to 0, we just have e to the 0, which is 1. And what do you know? That's a sub 0 over 2. Right? Because if you go to a sub 0, cosine of 0 is 1, and you have f of x, you're going over 1 over pi. So you can see that c sub 0 is equal to a sub 0 over 2. And then the other ones, we should be able to work out as well, okay, in either direction. And it's really just going to be to find the relation between the c's and the a's and b's. So suppose we were to do a sub k, we'll just take this definition here. But then we can do the cosine as e to the I kx plus e to the minus I kx over 2. Make sense? Problem is that I'm always giving away the whole game. But that's all right, because you actually have to look at it again for it to click. Okay? So yeah, I plugged in my definition of cosine that I've just been belaboring how important that is, right? And then what would we have? We would have a 1 over 2 pi if I pull that minus pi to pi. We would have f of x e to the I kx dx. And we also have 1 over 2 pi minus pi to pi. F of x e to the minus I kx dx. But what do you know? This is equal to c sub minus k. And this one over here is equal to c sub k. Oh yeah, that should be enough of a hint to just demonstrate the whole thing. Okay. So what we now have is these two equivalent forms. We can do it for real. This one is actually more general with complex functions. But otherwise they're equivalent. Okay. And sometimes one is more useful, sometimes the other one is more useful. For doing proofs and stuff, this one here is very useful, as we saw. Those integrals are easy. Anything else to be said there? That's not bad. Good. So yeah, you guys just have a closer look at this, and you get really nice practice working through these. Want to do the sign, you're going to have minus sign 2i and see what happens as well. Okay. And then you can relate the two. Good. So now let's do some exercises with this. And I think the first thing we're going to do is use this formalism and do our step function again. Do our step function directly. And then I'll check my notes for some more examples. So yeah, this is a homework. We got a good start on it. And I'll erase this. Actually, now we have these theorems. Let's go ahead and state this business with the odd and even functions explicitly. Okay. So we have the real Fourier series. Now, if f of x is an odd function, and that means f of negative x is minus f of positive x, then what happens to these a sub k's? Okay. You can do a formal proof, but visually, it's really clear. The cosine is even, and you've got an odd function. So if you break it up into two integrals, minus pi to 0, 0 to pi, one of them is exactly the negative of the other. Okay. Well, this is the one we used, right? This is the one we used before. And since one's, if you multiply this function by an even function, you're still going to have an odd function. And you're going to integrate that odd function over this symmetric interval. It's going to vanish. So I think I'm just going to write that down without further ado. What we end up with is a sub k is equal to 0 for all k. And if f of x is an even function, which means f of minus x equals f of positive x, so it's an even function, then you multiply that even function by an odd function sign and integrate from minus pi to pi, then the integral from minus pi to 0 is equal to minus integral from 0 to pi. So for that reason, without further ado, then a sub k equals 0 for all k. So now we're going to tackle that step function again. So what we know is we've got our step function. We're just going to be looking at these from the outset. And that can save you a lot of work. If you don't pay attention and you're doing all these integrals, and after all this work it turns out to be a 0, you could have skipped that work. That's definitely something to pay attention to. But yeah, always before you calculate, give it a little thought. Little thought. So now we're doing the step function again, that we did the other day. Step function. And I'll just draw it for the moment. Minus pi, minus 1, plus 1. Okay, so we've got that step function. All we have is the d sub k, so we're going to have f of x sum over d sub k sine kx, okay, equals 1 to infinity. Equals, so there's our definition. We'll already break it down. We're going to have 1 over pi minus pi to 0, negative 1 sine of kx dx, and then we're going to have 1 over pi 0 pi positive 1 sine of kx dx. So you know what? You guys just go ahead and do that one. Okay. You know what the answer is going to be. And you put it in the right closed form. And then we'll actually set up a more, not more interesting, but another one. Okay, set up another one. What you'll notice is this process is very basic. It can just be difficult if the integrals get difficult, but you can get a machine to do this kind of thing very well. And suppose you had some wild and woolly step function. I'm just going to make something up. Okay, terrible. But here, I'll draw some stuff over here. Maybe going over here. So you've got a step function that was, this. Okay, you don't want to do that by hand, but a machine can certainly do that. And then what would happen from, this is minus pi to pi, what would happen from pi to 2 pi, or pi to 3 pi? The whole thing would just repeat itself. So you could have some really wild step function thing, but what if this were a repeating waveform, like your electrocardiogram? Then apparently you could do an analysis like this as well. So what you're seeing is that you can break down, you can analyze something into its constituent waveforms. So we could do these basic ones by hand or analytically, and then more complicated ones you would have to have enlist the help of the machine. Okay, so let's leave these guys up here and try something a little different. Oh, and I think I mentioned the other day, function generators will give you a whole list of possibilities. They'll have this thing here, these square potentials, they'll have sawtooths, and so forth. So what we want to do is integrate up a couple of those. Sawtooth, this would be a repeating square. So yeah, let's do one more of these. Or a couple more. Just here's our next example. I'm going to start listing these just for homework. We'll get started on all of them. We'll start together. What if we have f of x equals the absolute value of x for minus pi less than or equal to x less than or equal to pi. So what if we have that function? First thing we want to do is sketch its graph. Got minus pi, pi. This time it's going to go up to pi. It's that. And since it's going to repeat itself, if you go out to 2 pi and 3 pi, you're going to have this all the way across left and right. So this is an even function, so we need the cosine. So we're going to have f of x is equal to a sub 0 divided by 2 plus sum over a sub k equals kx. You know, and the a sub 0 over 2 itself is interesting. Because that really just shifts the thing up and down. That's going to be an average value. So let's see what we have here. We've got 1 over pi, and then x. And here's something we can do as well. So x, we can do x dx from 0 to pi. And it's going to be the same on the left side, and so we can multiply that by 2. Times 2. So we have 2 over pi, 2 over pi, and then we've got integral x dx 0 to pi. 2 over pi 1/2 x squared. Zero to pi. So that's going to be pi squared over 2. So that's at a certain value right there. Okay. That's a0, and then of course we're going to actually have a0 over 2, and so we'll have pi squared over 4, which will be right through it. Yeah, so we've got that. What about the other ones? So, other ones we have to be a little more careful, but they're all just a sub k, so we will have a sub k 1 over pi, and what we can do is we're going to be f of x, so x goes to kx dx. Of course, you don't want this, you want to break this up into 2 integrals. Okay? You want to break it up into an integral minus pi to pi over pi. You want to break it up into an integral minus pi over pi, so I'm just going to write equals integral minus pi to 0 plus integral 0 to pi with the appropriate stuff there. And then we'll see what comes out. And a lot of these, you get, you'll see, you get alternating coefficients. You get some of the missing coefficients again, so you'll see when that comes out. Let's put another one up. Good question. Yeah.
Shouldn't our A0 be, I think you actually dropped it.
Oh, I dropped the 1 over pi? Oh, you're right, 1 over pi is here, so.
So that's, yeah, just going up to pi.
Exactly, pi over 2. And then pi over 4, thanks, yeah. Drop the 1 over pi, everybody correct that while it's still possible. So good, there's various and assorted ones, and I want to give a couple of these before we get some, next time, some general rules that we can, yeah, you know what, we'll do the, so I'm gonna, okay, so this is a homework problem, just to, did I say homework? I did not. So yeah, this is a homework problem to complete it. And I'm gonna do another one of these. So this was an odd one. We're just gonna do the obvious next example of an, I'm sorry, this was an even one. We're gonna do the obvious next example of an odd function. Let me just put a note here that I forgot to mention. So once you have higher powers of x here, you're talking about some kind of integration by parts. Okay? You're not gonna get away unscathed. You gotta do some integration by parts. We'll see later there are also options of doing parameter-dependent differentiation, but for now you're going to do an integration by parts, because you've got that x in there. You break it down, you get minus x here, plus x here. So I'll put that as a note. So when you tackle this thing, you do have to do integration by parts. And so you can see that each higher power we're going to put in there, we're going to have more trouble with it. More work with the integration by parts. But these next couple are good examples. So we've got our formulas up there. Let's look at the odd version, namely just a straight line. So this example that we'll also start and then put on the homework. We're just going to do f of x equals x from minus pi less than Okay, so here's something we can grasp pretty well. Minus pi to pi, this is the function. And its continuation, if you went to 2 pi and 3 pi, and of course the negative direction as well, would be like this. So actually what's going on is that you've got functions that are going here and then it's kind of an infinitely steep drop down to there, repeats itself. And that's why these Fourier series now function generator, if you had enough of those sines, cosines, in this case sines, then you would, with 10, 20 of them, you start approximating this really well. So let's look at what we have here. This time, it's just going to be b sub k sine kx. So a sub k is equal to 0 for all k. B sub k is equal to 1 over pi x sine of kx dx. And the series itself is going to have a solution b sub k sine of kx. So there's going to be something interesting about these that we want to take a look at. What is the value of the function at pi over 2? Note f of x equals pi over 2 is just equal to pi over 2. you're going to get a summation. I'm just gonna put this under here. F of x is equal to sum over b sub k sine of kx. K equals 1 to infinity. So f of pi over 2, so you're gonna get pi over 2 is equal to the sum of these b sub k's sine of k pi over 2. So that's sort of an alternating thing, because sine of pi over 2 is 1, 2 pi over 2 is 0, you get a minus 1. So you're actually going to generate this alternating series in terms of k whose summation ends up to be pi over 2. Now these are, I don't know if the mathematicians would love these to calculate pi because it would take a lot of terms. But these are examples of getting an expression for pi, right? In terms of an infinite series. So that'll be fun. Once you've got this thing knocked out, then you'll be able to get a pi over 2 equals sum over the big alternating, 1 over k squared, etc. Alternating series for that. So I'll put that there as well. So this homework problem, and actually before we do that, yeah, there's not that much more to be said about this one, right? You have to do the integration by parts, and then then you have the explicit b sub k, and once you have that, you can actually check the answer against this kind of thing you can look up Fourier series for. I'm tempted to do one more, but how many do we have? We now have a good set. What was due this week anyway? The ones we're going to talk about in the recitation, they were due this week?
Yeah, those were the only ones you assigned last week.
Only those two?
Mm-hmm.
Okay. Okay, yeah, so we'll add some of these. I'm not quite sure. We'll draw the line under them on Thursday. Right, for now, we can just keep piling them up. These are all good. Good calculations. So yeah, as far as the homework goes, you find all of these and then you've got a nice, you'll see the pattern, you can write it out for a few terms. And then as the bonus, find that expression of pi over 2. Okay. So homework, I want to find all these b sub k's, and then this homework here, expression for pi over 2. That's kind of an alternating infinite series or some type. You'll see when we get there. Okay. Let's see. This trick can be done repeatedly. Differentiation. Good, yeah, these just have to be practiced. Any questions or comments on these? I think that's a good set. So if you go back to the step function, you know that answer, you'll do it with the signs and you'll knock that one out. Then we have the absolute value one, which will be a cosines, and then we have this one, which will be sines again with a little bonus. I think I'm gonna add one more thing to this discussion, but this is, as far as the problems goes, a good set. Yeah. back to the complex version because it's the easiest to work with. Here's our question. How do we modify what we've done so far? Of course, it'd be better if we practiced it a bit, but how do we modify it if we have an arbitrary interval minus L to L over which we want to expand some function in a Fourier series? So we've just got some function here, and we want to take the formulas we have and just write them down for minus L to L. Probably the best thing to do is write down our complex formulas again and just kind of stare at them. Okay, so for minus pi to pi, we're just making use of the periodicity of the trigonometric functions. Let's have a look here. Suppose we had for minus pi, with our interval, we had f of x equals sum over c sub k pi kx plus infinity. And we had c sub k 1 over 2 pi f of x equal minus pi kx dx. So what do you think we're going to do for minus L to L? We could start either place. This is the length of the interval, so it will be 1 over 2L minus L plus L. We've still got a function here. And, you know, we've got k's, so minus I k, but now what? Remember, k is just an integer. Let's do it. X is equal to L minus ik pi, right? X is equal to pi minus ik pi. So that should do the trick. And then we would have f of x equals c sub k. And make use of that same periodicity. Equals I k L x. With or without proof, what do you guys think? You know, you could do that, you could now prove this by multiplying this, you know, doing that same calculation minus pi to pi. So maybe we'll do that next time with that proof. Now, these are functions of just x, which is some mathematical variable. What if we're talking about time? If we're doing these function generators, we're actually talking about frequencies and the times. So what we'll do next time is we'll actually make sure we know how to change these variables to time variables, time and frequency variables. You have to just be confident with all of them. But for the moment, this is a really important step, because eventually it's going to come pretty soon, we're going to take these limits out to infinity and be able to deal with functions that are defined from minus infinity to plus infinity. So that's an intermediate step there. But for the moment, that's enough. You guys just got to go out and practice some of these a bit. And that's all I've got for you today.